it. So thank you for coming for the third lecture by Maryna Viazovska, and she will talk on sphere packing, cyclotomic fields, and subconvexity bounds.
So let me start with recalling what I already mentioned in my previous lecture, namely the construction of these lattices. So how, if we have a number field, how do we construct lattices out of it? And so here we are using the very classical theory of the geometry of numbers. And so let K be our number field, and let OK be its ring of integers. Then our number field can be embedded into complex numbers, and the number of different embeddings will be equal to the degree of the field. And so some of these embeddings will be real, and some of these embeddings will be complex. And so then all complex embeddings, they will come in pairs related by the complex conjugation. And so the classical recipe is the following, is to consider the following real vector space, which will formally it would be the tensor product of our number field with the field of real numbers over Q. And then if you want to think of it coordinate-wise, so the natural way to think of it is the following way. So we'll take all our real embeddings and the half of our complex embeddings, so that each embedding is which up to complex conjugation will be represented once. And then for each element of the number field, we consider all of its embeddings, and this way it will land in this d-dimensional real vector space. So now this way we have created a real vector space, but now as we speak about lattices, we also want this space to have the structure of the Euclidean space. So we need to introduce the scalar product. And so a natural scalar product is the trace product. So if we take an element of the field, two elements of a field, what we can do, we can take the product of the first element and the complex conjugate of the second element, and then compute the trace of this algebraic number. And so this would be the scalar product. And so if you want to extend this to our real dimensional space, so this is essentially what we have to do. And here I think there is still some ambiguity in this notation, namely that here when I'm taking this the sum over all embeddings, here actually I'm taking, like for the pairs of complex embeddings, I'm taking both of them. And so yeah, in here it's like x with index sigma bar, it's the same as a complex conjugation of x sigma. So it's so that the resulting scalar product would be actually a real number. And so also what we would like to do somehow, if we take our ring of integers and look at its image under this embedding, what we will get a lattice inside of the Euclidean space. And now, so it's already a matter of taste a little bit, but here what I would like to do, I would like this lattice to be unimodular, to have covolume 1. And so this is why I normalize my scalar product with the suitable power of the discriminant of the number field. And so here are some simple examples of how this works. So of course the simplest, the most basic example is when our number field is just Q. And so of course then we know that Q lives inside of R. So it has one real embedding, and that the ring of integers would be just the ring of integer numbers. And of course it is a lattice inside of this real line. And so another example is a bit more difficult. So this is a quadratic field, Q adjoint square root of 5. And so in this case, we know how the ring of integers looks like. So it would be this two-dimensional lattice, which is generated by element 1 and by the element 1 plus square root of 5 divided by 2. And so we will get a lattice which is depicted here in blue points. And then for three-dimensional, for fields of degree 3, the Blackboard doesn't have enough of dimensions, so we will not give examples like that. But I hope you could grasp the main idea. And so now, of course, what is as we have this focus on the symmetries. So of course, for example, we can see that now the group of units of our number field that lives inside of this ring of integers, and it also acts on our Euclidean space by coordinate-wise multiplication. And because this is a group of units, it will fix our lattice OK. So it will be fixed by this action. And so if we have a unit of finite order, which somehow we have for this quadratic field, we don't have somehow interesting units of finite order. We have plus minus 1, and that's it. So the action by this finite units, it also will be an orthogonal action with respect to our scalar product. And so what we have done last time, we have considered the space of rank T3 unimodular OK lattices. And so such lattices, the space of these lattices can be realized as a quotient of this algebraic group by its discrete subgroup. And in fact, one can consider also more general lattices with these OK symmetries, but for our purposes, this space was already somehow sufficiently interesting, and all these other lattices, they will live in a very similar spaces. So what we have seen last time is that the random lattices from this space L KT, they satisfied the Ziegelweil theorem. And in particular, while one consequence of the Ziegelweil theorem that we have used is that the expected number for the number of points of such a lattice inside of a fixed ball centered at 0 will be equal to the volume of this ball plus 1. So here plus 1 stands for the 0 because 0 is an element of every lattice and always an element of the ball. And so last time we have seen that the corollary of this theorem is this lower bound for the lattice packing density. And so one question one might ask, so all this worked for lattice for this OK modules of rank bigger or equal than 2. And so also one can ask, so what for rank 1? Can we construct, first of all, can we construct this interesting family of lattices of rank 1? And then also would a certain analog of Ziegelweil theorem be true in this case? And so it turns out that all these are rather classical questions. And so as for the space of such interesting lattices, they are captured by what is called the Arakelov class group. And so this group can be defined in the following way. So let's consider the set of the following pairs. So the pairs of element G and I, where I would be some fractional ideal inside of K, and G be any element of our Minkowski space associated to K, such that all of its coordinates are non-zero. So that in the coordinate multiplication, it will be an invertible element. And so what we would say that two such pairs, they are equivalent if the element G multiplied by I1, it will be gommatetic to the lattice G2 multiplied by I2. So these are all this, so we take all fractional ideals of K, then we multiply their coordinates by different non-zero numbers, and so we look at all the possible lattices that we get, and then we look at their equivalence classes modulo the homotety, so multiplication by a positive real number. This way we will, it can be, so the, what we will get the following exact sequence of topological abelian groups. So here in the middle we will have our École class group, and so it can be, and elements in this École class group can be, so here this is the class group of our field, which is a finite group, and so for each element in the class group we will have this continuous space, which is essentially a torus. So this space here, this would be a d-1 dimensional torus. So for each ideal class, we will have the space of lattices, which will topologically look like a d-1 dimensional torus. Or it will be this set of elements in the Minkowski space which have such that the product of all coordinates is equals to 1, and of course this would be with respect to the multiplication, this would be a subgroup, and the image of all the units of our number field would be a discrete subgroup of this group. And so now our probability space, it would be this finite collection of tori. So it seems like a rather nice space to study. So now let me demonstrate to you how this works in an example. So in the two-dimensional example which we have seen before. So for this field Q adjoins square root of 5, so it has class number 1. So we have one element in the class group. So here, for example, the lattice of the lattice which corresponds to the ring of integers. And so now what we can do, we can take points of this lattice and multiply them. So multiplying one coordinate by a real number and another coordinate by the inverse of this number. And this way we will get a new lattice, and the new lattice, it will be still invariant under the multiplicative action of the group of units of our field. So this is somehow what happens. We are multiplying like this. So this way we will see that each point in the lattice, it will live on some hyperbola. And so once we multiply by a number which is an element of our group of units, we will just come back where we have started. And so this way we will see that our École group for this number field, it will be topological isomorphic to a circle. And so the question is whether whether we still can compute the number of the expected number of lattice points in a ball for ideal lattices. So here's the theorem we have proven with Nihar Gargava. So it turns out that the answer on one hand is we don't have an exact formula for the number of of such points, or rather we have an exact formula, but it is a rather complicated one. However, asymptotically, the expected number of points, it would be still very close to what we get for lattices of higher rank. So here again, the expected number of this theorem, it does not work for any field. It works for nice fields. In particular, it works for cyclotomic fields. So for what we have proven, that if K is a cyclotomic field and B is a ball inside of the Minkowski space, and the volume of this ball is big enough, then as the degree of the cyclotomic field goes to infinity, then the number, the expected number of lattice points of an ideal lattice inside of this ball will be essentially equal to the 1 plus the volume of the ball and plus an error term. And the error term will be small if as the degree of the field goes to infinity. And so, yeah, so we can estimate the size of the error term in the following way. So this, the size of the error would be smaller than the square root of the volume times the discriminant of our field raised to some negative power. And because as the degree of the number of cyclotomic number fields is growing, the discriminant also grows very, very fast. So that's why we can actually get an estimate, something like this. So this error here, it will grow, it will decay super exponentially in the dimension. And so now let me tell you how this formula was obtained. So this formula, like maybe it's like a small corollary from this is that, for example, this gives us improvement of Venkatesh bound by factor of 1/2, which maybe right now is not so impressive. But another way to view this result, that is a kind of an equidistribution of ideal lattices inside of the space of all lattices, or a weak form of that. And so here, how can we? So what are the main ingredients of our proof? So our proof is based on Heike's integration formula. So Heike's integration formula, it is one way to see it is corrected Siegel mean value formula for ideal lattices. So here we will see if we take again the expected value of if we take first a function f, which would be a nice, so compactly supported smooth function on our Minkowski space, and we want to compute the average, the expected value of the lattice sum function associated to this function f. Then as the answer, we will get the integral of the function f over the whole Euclidean space. So this is similar to what we've seen for lattices of higher rank. And we will also get an error term. And this error term, it will be expressed in terms of the Dedekind zeta function of our field, the class number of our field, the regulator of the number field. So this is all somehow can be nicely composed. Can be here it's stated as a volume of the Arkelov class group, but in reality the volume of Arkelov class group, this would be the regulator of the group times the class number. And here we have a contour integral of over a vertical line of a product of the Dedekind zeta function associated to our number field. and the Mellin transform of our function f, and this gamma factor associated to the field. And so now to somehow to control, so here, okay, so here is the curl of, you can apply that theorem to the indicator function of a ball. So it's not exactly a smooth function. So but if you do a little bit of work, it's still somehow, the formula still works. So we have done our homework and checked that the integral converges. And so I would get a similar formula. So here it's formulated for the totally imaginary number field, because we're interested in cyclotomic fields. So this is why we have formulated it for totally imaginary number field, but for totally real number fields, things will work in a very similar way. So there will be no major difference. And so we will see that this expected number of lattice points inside of the ball would be 1 plus the volume of a ball and plus this error term. And because in this case, for the indicator function of a ball, we can explicitly compute the Mellin transform. So we would have to, our error term will be equal to this contour integral over vertical line of Dedekind zeta function multiplied by this gamma factor. And so the last step that we have to do is to estimate the error term and to show that it is small. And so here, probably, even if you are not a number theorist, maybe you know that maybe you've heard that number theorists have special love for L functions on the critical line. So this line from where on the complex plane where the real part of complex number is equal to the 1/2, it's called the critical line. And number theorists very like studying Riemann zeta function on this line and other L functions as well. And the behavior of zeta function on this line is quite peculiar. So it is very, very oscillatory behavior. And we don't have, at the same time, the value of the zeta functions do not grow too much. So, and actually to knowing exactly how small they are. So this is a subject of very famous and very hard conjectures in number theory. But then, even though we don't know the exact behavior, we do have some bounds. There are bounds which are called convexity bounds. They're easy ones. And then there are subconvexity bounds, which are more complicated, more elaborate. And so here we are lucky. So in order to get some kind of nice result that we need, we do not need all the knowing the generalized Riemann hypothesis or knowing the it's like most complicated form. So the subconvexity bounds are already sufficient for us. And so, okay, so here is the plot which shows this behavior of various directly L functions on the critical line. So here in green, in red is the Riemann zeta function, and in other colors, these are other L functions of various conductors. So the conductors and the corresponding L functions, I've chosen them randomly to show you that, okay, we have this complicated oscillatory behavior. And I think here, if I remember correctly, this is the real part of the value. There is also imaginary part which did not fit to the plot. And yeah, so here you can somehow maybe see that somehow there is a lot of acceleration and not a lot of high peaks. And this is exactly what we would like to know about. And so here, what we were using in our work is the following theorem by Young and Petrov, where they prove a bound for the value of Dirichlet L functions on the critical line. And so they're bound. They depend on this positive number epsilon, and here they do not. The bound is true for some constant which depends only on epsilon and does not depend on the conductor Q, and does not depend on the T, which is the imaginary part of the point where we evaluate the L function. And yes, so here what is important for us is that we have bound in both the conductor and the imaginary part of the point where we evaluate our L function. And so here, as a corollary of this theorem is the estimate for a value of a Dedekind zeta function of a cyclotomic field. And here the way these two inequalities are connected is that the Dedekind L function of a cyclotomic number field, it is a product of Dirichlet L functions of various for various characters. So from the functoriality we can get this estimate for the Dedekind zeta function. And I guess probably here one thing which is missing is the absolute value. So this is an estimate, of course, of the absolute value of the number. And so, yeah, so here it's some kind of important for us that in this subconvexity bound, the exponent is actually 1/6. So this what makes things work for us. And so the conclusion of this first part is that random ideal lattices for cyclotomic fields, they're almost as good as random lattices. So they somehow, we have this collection of finite tori which sit inside of our space of random lattices, and they distribute in this space somehow uniformly enough so that at least as we're counting the number of lattice points in a ball, we do get like not the same result, but a similar, very similar result. And so, but then one can actually go look. So the second part is of my talk would be about a different question. Okay, so here, here I think I have a bit of a also typo. So it's, okay, so let's now look closer at the so not the modular but the module lattices of number fields. These are these lattices which have higher rank over okay, not rank 1 but higher rank. And so what kind of interesting things can we study about them? So here we draw inspiration from classical results about random lattices. And so here is a old result of Rogers about the distribution of the number of lattice points inside of a ball, but not only a ball, actually his theorem works for any centrally symmetric body. So if we take fix a centrally symmetric body in t-dimensional Euclidean space, and we consider random lattices without any additional structure in it. So again, with the numbers we are studying are the number of lattice points inside of this centrally symmetric body. So the question is, how is this random variable distributed? So from Ziegel-mean value theorem, what we know what is the expected value of this number, and then the expected value would be the volume of the body plus 1. And now the question would be, what is the or in this notation would be just the volume of the body. And now the question is, well, but there will be, of course, there will be some fluctuation around the mean value. So what what the distribution will look like. And the answer which Rogers obtained is actually a quite natural one. So the distribution would be the Poisson distribution. So if we had somehow a random point process of the same density as our lattices, then this would be the number of points that we expect inside of the body. And now if you do this, so the random lattices, in a sense, they for this counting problem, they are very similar to the Poisson point process. And so how Rogers does it? He does it by computing the moments of this random variable. And so he can, so for if we are in dimension t, then he would be able to compute, roughly speaking, square root of t moments, and show that these moments, they will be close to the moments of the Poisson distribution with some small error. And so this error, it will be small if n is, so the number of our moment n is smaller than square root of t, or much smaller than square root of t. Then this will be a small error term. And of course, also for this to work here, some of the quality of this estimate will depend on the volume of our set V. And so, okay, so this is how the Poisson point process looks like. So, yeah, no, probably not. But I think it's not specified, so probably not. And so, of course, now the question is, can we reproduce this result for lattices with symmetries? So will this still get something like this? And on one hand, we know that, of course, we have, as we have seen already last time, if we have a lattice with symmetries, then the number of points in a ball, it will come in these packages. In packages, and the size of the package will be equal to the number of finite elements in the unit group of the ring of integers of the number field. And so for this reason, we probably have to somehow ask for something else, so we cannot have a Poisson process, but maybe if we compute not the number of points, but number of points divided by the size of this finite group, maybe that number will be will follow the Poisson distribution. And so, okay, so the answer to this question is that, in fact, the answer will depend on the number field we are talking about. So there will be some very nice number fields, for example, like cyclotomic fields. And there we could answer this question positively, and there will be some not so nice fields where we will not be able to answer it positively. But then maybe before I go to that, let me probably formulate the question a bit more precisely. So because now we are in this complicated situation when everything is changing, our dimension is changing, the field is changing, the OK rank is also something we might be choosing. Okay, so here, working together with Nihar, Gargava, and Vlad Serban, so what we have found that if we fix the degree of the field and then let the rank of our lattice over OK over the, so if I fix the field and let the rank grow, then it will be very easy to generalize the theorem of Rogers, and then we will get Poisson distribution for all lattices. So here, of course, again, we will have some The only thing that will change is that our computations, they will work when rank is big enough, and the rank has to be big enough comparing to the degree of the field. But then it's maybe not such an interesting generalization. So I thought that the generalization we would really like to see is the situation when we fix the rank and change the number field. So this would be an interesting direction to generalize. And so, for example, on our journey of doing this, we were able to prove the following result for cyclotomic number fields. So if we have a sequence of cyclotomic number fields, and we fix a rank of our lattice, of our OK modules to be at least 27. So here 27 is okay. I hope that I think now we worked on improving 27 and now we are almost done. So okay, 27 should be something smaller. So ideally 3, but now it's like 8. So, and then if we fix this rank and go over our sequence of cyclotomic fields, then, for example, the second moment for the number of points of the OK lattice, it will be very close to what we should. So this is the second moment of the Poisson distribution, and so on the other hand, it will be bounded by the same quantity plus this small correction term. And so here is a more, okay, but then somehow, so things work for cyclotomic number fields, but then the question is, what are the other nice number fields for which such a result would be possible? And of course, we proved that we will be able to do this not only for the second moment, but also for higher moments, modular some more technical conditions. And so here it turns out that it will be important to, if we fix a number field, it will be important for us to know whether this number field contains elements of small Malner measure. And so like elements of small Malner measure, they will be the enemies of Poisson distribution. And so let me tell you what the Malner measure is. So let K be a number field and let alpha be a non-zero element in our number field. Then we can embed, we consider all the valuations of this number, and so we take a product over all places of our field of a maximum of 1 and the evaluation of our number. And so this is what is called the Malner measure of an algebraic number. And so what can be interesting also for us from what we have already done is to look only not at the all places, but only at the infinite places. So here it means that we need to look at all complex embeddings of alpha and look at their absolute value. And then out of those we choose we take a product of maximum of 1 and this the absolute value of alpha. And for example, if our alpha was an algebraic integer, then the Malner measure will consist only of this product of contributions from infinite places. So contribution from all finite places will be 1. And so another maybe useful way to, so this is a useful definition, but then it has one somehow shortcoming, is that we have one number alpha and consider it inside of different number fields. Then here the Malner measure defined in this way, it would be a different measure. So we would like to give some definition which depends only on the algebraic number alpha and is not dependent on the number field in which we are looking at this number. And so it's nice to look at this normalized version, and also as we are normalizing, we will also look at the logarithmic version of this product. And so this is what we would call a Weyl height of an algebraic integer. And so now a good thing is that now the absolute Malher measure and the absolute Weyl height, they will be independent of the field in which we are considering our algebraic number. And so now the question is how small this height can be. And so there is a famous Lemmer's conjecture which asks us whether this number, the absolute Malher measure multiplied by the degree of alpha, whether this has some uniform bound from below. And this is a very difficult open question, but what we will need, we will actually ask for fields with a stronger property. So we'll ask for fields which satisfy the Bogomolov property, and we say that a subset of algebraic number satisfies Bogomolov property if there exists a positive constant such that all elements in this set have absolute Malher measure bounded from below by C. And so, of course, now the question is if Malher conjecture is something much weaker and it's still so difficult, do we have number fields like this? And it turns out that yes, we do have number fields like this which satisfy this stronger Bogomolov property. And so here, so what are those nice examples? So those nice examples are, for example, the totally real algebraic numbers. And so totally real number fields, they are number fields which have only real embeddings. So for example, the field Q adjoins square root of 5. This is an example of a totally real field. It has two real embeddings. And so there is a theorem of Schnitzel, which tells us that that for each, if number alpha is of infinite multiplicative order, so if alpha is not a root of unity, and it is contained in a totally real number field, then its absolute Malher measure is bounded by this number, which is the and so and then the same is also true for complex multiplication fields. And so there is another result of Amorosa and Dvornicic, and it tells us that also cyclotomic fields, they also satisfy the Bogomolov property. So if we have an algebraic number, and if this number has infinite multiplicative order, and it is contained in an abelian extension of Q, then its absolute Weyl height satisfies this lower bound. This is bounded by below, also by some number. And so now, so the result we have proven together with Mihar Gargava and Vlad Serban is that if we have a sequence of number fields which satisfy the Bogomolov property for a certain constant, then we can show that the nth moments for the number of points in a ball will be close to the Poisson distribution. And so here, of course, all this, so here there are some technical conditions which work, which we need to know. So this bound, it works for if the number of the moment that we are computing, it has to be low enough compared to the OK rank of our lattice. And also the OK rank of our lattice has to be big, big enough yes, so And now maybe another interesting question is, okay, so this Bogomolov property, we know that it's not true for all the number fields. So are there some number fields where we cannot hope for any kind of Poisson distribution, or we need to somehow redefine a new version of it? And so here we also found a counterexample. So it would be a sequence of fields, and this sequence of fields, they defy the Bogomolov property. And so as they defy the Bogomolov property, we can prove that the second moment for the number of points would be somehow by a constant bigger than what we expect for the second moment of the Poisson distribution. So if we have these fields which have elements with a small Malner measure, then we can show that there will be no Poisson distribution. So the second moment would be too big. So here's also some applications which we can have. So if we know about this moment, is there something useful? Like what kind of application this can have? And so one kind of applications is that to estimate the process, we can take a random lattice. And we look at the shortest vector. So maybe we would like to estimate the probability that this shortest vector is long enough, or it's. So here is the theorem, analogous theorem for the space of random lattices. So it was proven by Jian Wei and Peng Guan. And so what they show is that if the dimension of our Euclidean space goes to infinity, then with a probability near close to 1, the length of the shortest vector, so here it is normalized by the radius of a ball of unit volume in dimensions d, so it will be constrained between 1 minus this small error term which goes to 0 as d goes to infinity, and plus this small error term. So with probability 1, the shortest vector will have this length which is close to average. And so now if we can compute, since we now are able to go to compute the second moment for cyclotomic fields, so for lattices with the symmetry of cyclotomic fields, so we can prove the following result. And so this is joint result with Nihar Gargava, Vlad Serban, and Ilaria Avriglino. So let T be again our rank, and for technical reason now it's bigger or equal than 27, but okay, I hope that soon it will be 8, and should be in principle it should be 3. So and so let K be a cyclotomic field of degree. So with cyclotomic field, and let D, so this time our dimension of the Euclidean space that we are considering would be T times the degree of the cyclotomic field. And we consider the space of random lattices of in this space. So and then as the degree of our field goes to infinity, then with the probability close to 1, again the length of the shortest vector would be close to its what is expected from the closer to this. So then if it is normalized by this number gamma d, which is the radius of a ball of unit volume, then our shortest vector will be this number plus minus a small error term which goes to 0 as the degree of the field goes to 0. And so this is all I wanted to tell you about today. So thank you very much, and I'm happy to answer your questions.
Thank you, Maryna. Any questions?
You mentioned yesterday trying to do analogs of this for non-commutative rings, like quaternion algebras. How much of these moment estimates carry over in that case?
Yeah, so we did not try to do it. So yeah, so for example, I really don't know whether any kind of Schinzel result or Ambrosio-Dvorkovich result is known in that case. So I think like certain technical aspects would certainly could be preserved, but then yeah, so we did not really try to do that. So
The advantage there was just that you could, like, you can get better. Yesterday you were talking about trying to do this in certain circumstances. Like, why were you looking at quaternion algebra lattices?
no, so actually we looked into quaternion algebras just to see what kind of things we can get in there, and then yeah, maybe like secretly we did hope that they will get us like better estimates than from cyclotomic fields, but then they did not give us better estimates. But, I mean, I think they're still interesting because, for example, in thinking cryptography, people sometimes also looking in those kind of lattices. So, for example, maybe this last result which I showed here, maybe it would be interesting to have it actually for also other symmetries for the I don't know to help cryptographic community in. Yeah, but at the same time, it seems like it will be technically difficult. So yeah. Yes.
Other questions?
In part 1, if there would be a further improvement to the subconvexity bounds, would that improve your result, or is the 1/6 exponent is enough for?
So I think like I mean, we could have better bound on the error term maybe, but probably it would not be somehow like maybe the most important like critical thing was for this like integral to converge somehow, and then after it converges, it's already yeah. But then okay, what would be of course always interesting to have these results for other families of L functions, and like we could compute some kind of higher moments, and then they also will be related to other L functions. So if for those we had some kind of subconvexity results, it would be interesting, for example.
Thank you.
So if not, let's thank again Maryna for the 3 lectures. That ended up touching a lot of different areas of mathematics. So thank you, Maryna.